Hello, guys. Uh, I'm really disappointed with the number of people turning up for lectures. It's really, it's really important that people do turn up for lectures, right? Just because I'm being nice to you with the podcast doesn't mean that it's not an excuse for not coming to the lectures, guys. I'm waiting for the guys from the technicians to come and fix these things. do that before every lecture. I would appreciate that, sir.
Yeah, we do, but I'll show you how to do it, and then
No,
you'd know how to do it. You just press visualizer and then send it to whatever screen you'd like.
Yeah.
You with me? So that's that one. And then this is the new one. So laptop input, and we can send that to that screen. So if you just select your source, and then you can send it to whatever screen you want, if you're with me. No problem. So you've got, there you go. Laptop input, main screen. Okay?
All right, thank you.
No problem, mate.
All right, thank you. All right, I'm sorry for the delay, guys. Sorry for the delay. Last Wednesday, I started doing examples involving more than one parameter. And unfortunately, I was able to do only one example. Now, so what I'm going to do this week, that is today and tomorrow, I'm going to do more examples that involve either two or more parameters, right? The example I did last week was on the normal distribution. That is, when you have a normal distribution with two parameters, both are known, how do you find their MLEs, or maximum likelihood estimators, right? I'm going to do more examples like that today and tomorrow, okay? I mean, as you know, you learn things by examples. In every course in mathematics, you learn things by examples, okay? So the first example I'm going to start by looking at today is the following. Suppose excuse me. Right. The first example is the following. You have two random samples. The first one is x1 to xm IID with this distribution. The second one is y1 to yn IID with this distribution. And we are assuming that sigma squared is known. So the value of sigma squared is known in advance. So the only parameters that are not known are mu x and mu y. So what we have here is a two-parameter problem. So we need to estimate two parameters, that is mu x and mu y, right? So the first thing you need to do is to maybe it's too large. The first thing you need to do is to write down the likelihood function of the two parameters mu x and mu y, right? Because in this case, as I said, we have two parameters that are not, both of them are not known. So the likelihood is a function of two parameters. So you see, the likelihood is the product of these two. Basically, because you have two different samples, the first product corresponds to the first sample, right? So this one is the contribution from the first sample. So if I may write down here, guys. So this is the contribution from the first sample, right? And this one here is the contribution from the second sample, right? So the likelihood is composed of two parts. The product, the first is the product of the sample of observations from the first sample, and this is for the second sample, right? Now, if you simplify these two guys, you will get the following. You will get yeah. So once again, it's really, really important. I think I've said this many times already. It's really important that you learn to simplify products correctly, because if you get this step wrong, then everything else you do will be wrong too. Okay. All right. So it's really important that you get this step correct. Okay. All right. The next thing to do is to take the log of the likelihood. All right, this is the log of the likelihood function. And the next thing is I'm going to put this over here, guys. So hopefully you can see this. Because we have two parameters, mu x and mu y, we need to find the partial derivatives. First with respect to mu x, and secondly with respect to mu y. All right? So I'm going to first find the partial derivative of the log likelihood. First with respect to mu of x, right? So if you do that, guys, you get minus, excuse me. All right, this is the partial derivative with respect to mu x. Obviously, you can simplify this to this. And similarly, the partial derivative with respect to mu y, yeah, will be equal to will be equal to this. Yeah. So you have these two partial derivatives. The next step is to set this to 0. So let me set this to 0 and set this to 0. Call this equation 1. Call this equation 2. Right. Now from equation 1, you can see that that the sum sorry guys, sorry. So from equation 1, you can see that the estimator for mu x, the estimator for the first of the two parameters mu x is equal to x bar. X bar is the mean of the x's, right? And similarly, from equation 2, you can see that the estimator for mu y is equal to is y bar, that is the average of all the y's. Okay. So we found the estimator or the maximum likelihood estimator for mu x and the maximum likelihood estimator for mu y. And to actually formalize the result, you need to do the second order derivatives, but that will be complicated because, as I explained to you guys before, that will involve finding the determinant of a matrix, and I really don't want you to do that because in the case of an exam, that will take you a long time and you wouldn't be able to finish it. All right. So in this case, whenever you have a situation where you have more than one parameter, like in this case, it's okay to leave it like this and say that this and this are the maximum likelihood estimators for mu x and mu y. Okay? Is that clear, guys? Yeah. Okay. So it's okay to leave it and stop at this stage. Okay. Any questions so far, guys? You all right? Yeah. So this is just a second example I wanted to do. Now, let me show you one more example where I think this is something should be familiar to you. You should look at the Yeah, here we are. So this is another example. So here you have, once again, you have two parameters, A and lambda. Do you guys remember this distribution? We talked about this before. What's this distribution, guys? Huh? You already forgot or what? Huh?
Gamma.
Yeah, gamma, exactly. Yeah. It's the gamma distribution with the parameters A and lambda. It's on page 8 of the lecture notes. You should look at page 8. We show you what it is. This one here. Do you guys remember this? Yeah. Right. The first thing you need to do is to write down the likelihood function, which in this case involves two parameters, A and lambda. So this will be the product Yeah, this is the product of the density function of the gamma distribution. Yeah. So this is yeah. So this is the it simplifies to this, okay? Taking the log likelihood, all right, this is the log likelihood of the function. Now, once again, we need to do a partial differentiation with respect to the two parameters. So first, I'm going to do the partial differentiation with respect to parameter A. So that will give you n log lambda minus n plus okay. So this is the partial derivative with respect to A. The partial derivative with respect to lambda is will be this, all right? Now I'm going to equate this to 0, equate this to 0, call this 1, call this 2. Okay, let me switch over to here. Now, before I proceed, I need to introduce. Before I proceed, I need to introduce a terminology. Excuse me. There's something, excuse me, there's something known as the Digamma function, and is defined as the derivative of the log of the gamma function. So is d by dA of the log of the gamma function, right? I'm going to use that here. So because from equation 1, what you have in equation 1 is n log lambda minus n yeah excuse me. And what you have from equation 2, you can say that lambda or in other words, you can write it as A divided by the sample mean, right? Okay, guys. Now, I'm going to call this equation 3. I'm going to call this equation 4. Sub 4 into 3 to get. I'm going to short for substitute, okay? If you sub 4 into 3, you get n log of A divided by x bar minus n equal to 0. Yeah. And this is the same as n log A minus n okay. All right. And call this equation 5. Right, call this equation 5. Now, obviously, you cannot simplify this further, right? Can you? I mean, can you guys simplify equation 5 further? Because I mean, remember the idea is to find a solution for A and a solution for lambda. There are two parameters, A and lambda, right? Now, this equation, it involves only A, but there are two places that there's an A here, and there's an A here, which is an argument for the Digamma function. So you can't, but looking at this equation, it doesn't look easy to solve it, right? Or does it? Doesn't look easy, right? So basically, what you have to say is that the MLE of A is the root of equation 5. is the root of equation 5. And that root may have to be computed using a package or computer software or something like that, right? It's something, I mean, it may be done by a calculator even, I don't know. And the MLE of lambda, say lambda hat, yeah, is equal to A hat divided by x bar. Yeah, that's because of equation 4, guys. Remember, from equation 4 says that lambda is equal to A divided by x bar. So the MLE for lambda is the MLE for A divided by x bar, right? So this is the conclusion. These two statements here, give you the answer to finding the MLE for A and the MLE for lambda. Now, the reason I have done this example, the reason is because, I mean, it's something I'm going to tell you, but very few people, well, it's one of the most recent, developments in the statistical methods literature, right? There were two guys from Singapore. They wrote a paper which was just published 2017, and in that paper they actually showed that this equation here, this is just hot topic, all right, hot news. 2017 in the journal this journal is online. You'll be able to access it online. It is called the American Statistician. That's the name of the journal is called the American Statistician, and there is one of the latest issues of this journal. There was a paper by two guys from I think they are maybe lecturers or I don't know. The two guys from Singapore. They published a paper. And they showed that this equation here, which I call equation 5, right? Right? What they showed in that paper is that the equation 5, which is this one here, right, does have a solution for A, and it's not just any solution. The solution for A that equation 5 gives is a closed form analytical function. It's a closed form analytical solution for A. In other words, what they showed is basically that you can get a neat expression for the MLE for A, right, and for the MLE for lambda. So this is, this is a very, very, very beautiful paper. I think you must read this paper, guys. I think because the mathematics they used in that paper is very simple. Nobody has thought about this before. It's very simple mathematics they used in that paper, and they showed that this equation can be solved to get an elementary expression for A. A is the only unknown parameter in this equation, guys. Please, I ask you guys to read go online to this journal, the 2017 edition of this journal, and look at it. I mean, they've done it in a very beautiful way. And it's not beyond your mathematics. The mathematics they used is simple, elementary, right? I'm sure you can read it, right? So please go and look at it, right? All right, guys. So that's the reason I did this example, because I just wanted to talk to you about it, guys, right? So when you get home today, just make sure you go to that journal and read the paper. If you can't find the paper, let me know. I will just download it and send it to you. Okay. Okay. So all right. Next example. The next example is the following. Right, so here, once again, we have a two-parameter case where you have a random sample from, do you know what ln means? I'm sure you guys recall. It means what? Log normal, right? ln is the log normal distribution with parameters mu and sigma squared, and we want to find the MLE of mu and sigma. So the first thing to do is to write down the likelihood function, which is do you guys remember the density function of the log normal, right? Is 2 pi right? This is the density. I mean, if you look back in the lecture notes, guys, you will see this. This is the density function of the log normal distribution, right? Yeah. Now, the product here simplifies to this, guys, okay? The next step is to take the log of the likelihood, so the log of this, sorry. All right, so this is the log of this function. Next step is to find the partial derivatives is first with respect to mu and then with respect to sigma. So this is the partial derivative with respect to mu, guys. You can simplify this a bit. It will become all right. This is the simplest form you can get to. Right. Next, the partial derivative with respect to sigma is all right. So this is the partial derivative with respect to sigma. So set this to 0, set this to 0, call this equation 1, call this equation 2. Okay. Right, from equation 1, you see that this, which is equal to this is equal to 0. So the estimator for mu, which I call mu hat, is equal to this. Yeah? Okay, guys. Now, from equation 2, if you look at equation 2, guys, you will see that the sigma squared hat, right, is equal to 1 over n okay. And I'm going to replace mu hat by this thing here. So this would be 1 over n all right. So this is the estimator for sigma squared, and this is the estimator for mu, and this one is the estimator for sigma squared. All right, guys. Yes, any questions so far? I'm going to just do one more example for today. I know we started late, so let me do the last example for today. The last example is the reason I'm doing many examples is, I mean, you learn more from examples. than anything else. Okay, guys? Okay? So suppose do you guys know this distribution? This is what? This is the beta distribution, right? Which we talked about a while ago. So the likelihood function is the product yeah, this is the likelihood function, right? So taking the product, you see it is excuse me. Yeah, this simplifies to this. The second step is to take the log of the likelihood function. So that will give you minus n log of, this is the beta function, plus a minus 1 times this, plus b minus 1 times the log of 1 minus xi. Right? I'll be finished in a few minutes, guys. The next thing to do is to take the partial derivative with respect to a and with respect to b. With respect to a, it will be n So this is the partial derivative with respect to a, and the partial derivative with respect to b will be okay, right? And call this equation 1. Set this to 0, set this to 0, call this equation 2 and 1, right? So then the MLEs of A and B are the solutions of these two equations. So basically the equations being this is the first equation, which is equation 1, and the second equation this is basically equation 2, guys. Now, an open problem in statistics is that these two equations have yet no analytical closed form solutions. But if you can derive analytical closed form solutions for this, I think you will become as popular as the two guys I mentioned earlier. You know, yeah. If you can try to solve this, crack these two equations to find closed form analytical solutions to them, I think that will be a really big result in the statistical methods. literature. All right? I'll see you guys in a few minutes. Tomorrow I will do more examples when you have 3 or more parameters. So far we only looked at the scalar case and the 2-parameter case. Right? Tomorrow we will do 3 or more.